If you really look at the universe, I mean, the raw, unfeeling physics of it, there's a rule that it always wins. It's the second law of thermodynamics. It's entropy.
The tendency towards disorder, yeah. The statistical certainty that everything will, eventually fall apart or mix together.
Exactly. It's the reason that if you pour milk into coffee, it mixes. It wants to become this uniform, beige liquid. It never, ever unmixes on its own.
The universe just craves that equilibrium. It hates separation.
But today, we're talking about the one thing in the known universe that successfully, actively rebels against that law.
Life.
Life is, at its core, a chemical act of defiance. To be alive, a cell has to stand up to the entire universe and say, no, this stuff is inside me and that stuff is outside, and they're going to stay chemically different.
And to maintain that separation, to hold back that crushing force of entropy, you need a border.
But not just a wall, right? A wall is static. A wall is dumb. We're talking about something much more sophisticated.
We're talking about an intelligent interface.
Welcome back to the Deep Dive. Today we are looking at the border control of life, biological membranes and transport. This is Biochemistry 11 in our series, and to really get this right, we're synthesizing two absolute giants of the field.
We have Leninger's Principles of Biochemistry right here. This is what's going to give us that deep structural logic. The physics, the thermodynamics, the real nitty-gritty of why the membrane acts the way it does. This is the why.
And to answer the all-important so what question, we also have Harper's Illustrated Biochemistry. This brings in the medical context. What happens when this border control fails?
Right. Why do these failures lead to devastating diseases like cystic fibrosis or, major heart problems?
Now, before we get into the molecular weeds, we had to put up a quick disclaimer. We're synthesizing thousands of pages of incredibly dense science here.
We're essentially building a conceptual map for you, a way to navigate the material. But, as the saying goes, the map is not the territory.
Exactly. If you really want to see the beauty of these systems, and I mean the actual diagrams, the crystal structures, the clinical tables, you have to open the books.
You need to see the chapter on biological membranes and transport in Leninger and the corresponding chapter in Harper. We're here to explain the logic, but the texts themselves are the source of truth.
So this rebellion against entropy, this border, where do we even start?
Well, let's start with the architecture, because I think most of us, from high school biology, we have this mental image of the cell membrane. You look at it under an electron microscope.
And you see a sandwich. It looks like two dark lines with a light space in the middle.
That railroad track image, yeah. And honestly, that image probably set the field back for a little while. That static picture made scientists think the membrane was this rigid, fixed thing.
Like protein bread on the outside and a lipid filling.
Exactly. It looked solid. It looked like a plastic bag, something static.
But that's just wrong.
It is fundamentally incorrect. The model we've worked with since 1972, from Singer and Nicholson, is the fluid mosaic model. And the key word there is fluid.
So you have to stop thinking of a wall.
And start thinking of a sea, a two-dimensional ocean.
An ocean. So the barrier isn't a solid structure.
No, not at all. Under normal body temperature, it has the viscosity of, say, light machine oil or olive oil. It flows.
Yeah.
And floating around in this lipid ocean are proteins like icebergs or little boats or buoys.
And they can move.
They're free to drift around. The whole thing is dynamic.
Okay, this is the part I want to drill into right away because it feels so counterintuitive. If it's a liquid, if it's basically oil, what holds it together?
Right. Why don't our cells just dissolve into a puddle on the floor?
Yeah, if I put a drop of oil in water, it can break up into smaller droplets. What keeps the cell membrane intact?
That brings us to one of the most important and I think most misunderstood concepts in biochemistry, the hydrophobic effect.
Oh.
Most people think the oily lipid tails stick together because they like each other, that there's some kind of attractive force, a like attracts like principle.
That's what I was taught, that oil and water don't mix because the oil molecules want to be together.
That's the shorthand, but the physics is actually the other way around. The lipids aren't sticking together. They're being actively pushed together by the water.
By the water. How does that work? Unpack that for me.
Okay, think about entropy again. Water molecules are polar. They love forming hydrogen bonds with each other. They're constantly tumbling, rotating, flickering. They're chaotic.
High entropy. They're free.
Exactly. Now imagine you drop an oily, non-polar molecule into that party. The oil can't form hydrogen bonds. It's like a rock in the middle of a dance floor.
Okay.
The water molecules right next to that oil can't tumble freely anymore. To maintain their network of hydrogen bonds with other water molecules, they have to arrange themselves into this highly ordered, rigid, cage-like structure around the oil. It's called a clathrate cage.
So the water surrounding the oil is, of course, to become ordered. And we just said the universe hates order.
Precisely. It is an energetically expensive, low-entropy state for the water. The universe wants to fix this. It wants to maximize the water's entropy. So how does it solve the problem?
It has to get rid of the oil or hide it.
It pushes all the oily tails together into one big cluster.
Because that reduces the surface area that's touching the water.
Exactly. By clustering all the lipids, you minimize the surface area of oil that the water has to form cages around. That frees up the maximum number of water molecules to go back to being chaotic and happy.
So the membrane is held together not by the lipids loving each other, but by the water's desperate desire for freedom, for chaos.
That is the thermodynamic glue. And Lehninger makes a really key point here. This property makes the membrane self-sealing.
What do you mean by that?
If you take a micropipette, poke a hole in a cell, and then pull it out, the membrane doesn't shatter like glass. It flows back together instantly.
Because exposing those oily tails to the water is creating order, and the water immediately pushes them back together to hide them again.
You got it. It's a self-healing liquid shield. It's absolutely brilliant.
Incredible. Now, that's the universal physics of it. But Harper points out that while the physics is the same, not all membranes are created equal. They're not just generic wrappers.
Not at all. The composition tells you the function. If you look at the ingredients list of a particular membrane, you can pretty much deduce what that cell's job is.
And Harper focuses on the protein-to-lipid ratio for this.
Yes, that ratio is a huge clue. Let's take the extremes.
Okay, give us one extreme.
Myelin. This is the sheath that wraps around your nerve axons. Its one and only job is electrical insulation. It needs to stop ions from leaking out.
So it's basically the rubber coating on a wire. You don't want any machinery, any holes in it.
Exactly. So myelin is about 80% lipid. Very, very little protein. It's just a passive fatty barrier.
Okay. And the opposite end of that spectrum.
The inner mitochondrial membrane, this is the metabolic factory of the cell. It's where oxidative phosphorylation happens. The electron transport chain is running. It is a beehive of activity.
So it must be packed with machinery.
It's nearly 80% protein by mass. It's barely a lipid bilayer anymore. It's more like a solid wall of enzymes and transporters that are just held together by a little bit of lipid glue.
So if I hand you a membrane sample and tell you it's high in protein, you know it's a metabolic workhorse.
Immediately. And if it's high in lipid, you think insulation or just passive barrier.
Harper also talks about sidedness, that the membrane has a distinct inside and outside, and they aren't mirror images of each other.
That's asymmetry, and it's absolutely vital. A great example is the sugar coating. All the carbohydrates, the glycolipids, and glycoproteins.
Yeah.
They are found exclusively on the outer leaflet, the side facing the outside world.
This is the glycocalyx.
Yes, and it acts like a cellular ID card. It's how your immune system recognizes self versus non-self. It's involved in cell-to-cell adhesion. If those sugars were on the inside, facing the cytoplasm, they'd be completely useless for identification.
So the membrane has a very specific face. It shows the world.
A very specific face. Now, let's go back to that fluidity concept. Lehninger really goes deep on this, on phase transitions. It sounds like the cell is on this constant tightrope walk between being too solid and too liquid.
A razor's edge, yeah.
Lehninger describes two basic states, the liquid-ordered state and the liquid-disordered state. The easiest way to think about it is the difference between a block of cold butter from the fridge and a bottle of olive oil on the counter.
Okay, so if the membrane becomes like cold, butter solid, then nothing can move. The proteins are frozen in place, transport stops.
And the cell dies. But if it's like olive oil, too disordered, too fluid, it becomes leaky, it can't maintain a proper barrier, things can just slip through.
So the cell needs to be right in that sweet spot, a kind of gel-like fluid state. Flexible, but still tough.
Exactly.
So how does a cell control that? Let's say I'm a bacterium and the temperature suddenly drops. I'm in danger of my membrane freezing solid. What do?
You change the recipe of your lipids. Specifically, you alter the fatty acid tails.
Ow.
If you build your membrane with saturated fatty acids, those are the straight hydrocarbon chains, they can pack together very tightly. Think of stacking Pringles in a can.
Very neat, very ordered, very solid.
That makes the membrane more rigid, more solid-like. So if you're getting cold, you want to avoid that.
So you'd want unsaturated fats.
Exactly. You want unsaturated fatty acids. They have kinks or bends in their tails, usually because of a cis double bond. Those kinks act like elbows, pushing their neighbors away.
So they can't pack together so tightly.
You can't stack bent Pringles neatly. It creates space, it introduces disorder, and that maintains fluidity even when it's getting cold.
So a microbe living in a hot spring will have a different membrane composition than one living in the Arctic Ocean.
Absolutely. It's called homeoviscous adaptation. They are constantly remodeling their membrane lipids to maintain that perfect viscosity for whatever temperature they're in.
And then for us, for animal cells, there's the wild card, cholesterol.
The fluidity buffer. Cholesterol is just fascinating because it does two completely opposite things depending on the temperature. It's this rigid, planar sterol that slots itself in between the phospholipids.
I really like the analogy we talked about before we started, that cholesterol is like the chaperone at a middle school dance.
It works perfectly. So when the temperature is low and all the lipids want to huddle together and pack tightly, cholesterol gets in between them. It breaks up that tight packing.
It's telling the kids, all right, leave some room for the Holy Spirit. No hugging too tight. It keeps things fluid.
Exactly. But then at high temperatures, when the lipids are moving around really fast and the membrane might get too runny and fall apart.
The chaperone steps in again.
That's right. Cholesterol's rigid, flat ring structure grabs onto the fatty acid tails and restricts their movement. It says, okay, settle down, no running wild. It limits the fluidity.
So it prevents freezing at low temps and prevents melting at high temps. It broadens the safe operating range for the cell.
That's why it's a buffer. Without cholesterol, our cell membranes would be incredibly fragile and sensitive to temperature changes. It's a brilliant stabilizer.
Okay, so we've got this fluid, dynamic, self-healing sea. But just how dynamic is it? That brings us to our second section, the actual dynamics. Leninger makes a huge distinction here that I think is really easy to miss if you're just skimming the chapter.
We have to separate two completely different types of movement. There's moving sideways, and then there's moving across.
Let's start with sideways, lateral diffusion.
Lateral diffusion is incredibly fast. A single lipid molecule can move from one end of a typical bacterium to the other in about 1 second. The proteins are a bit slower, like big ships, but they're constantly shuffling positions.
So the surface is just constantly rearranging itself.
Constantly. But transbilayer diffusion, or flip-flop, which is moving from the outer layer of the membrane to the inner layer.
From one side of the sandwich to the other.
That is, for all practical purposes, thermodynamically forbidden. It's incredibly slow.
Forbidden? Why? What's the problem?
Think about the structure we just built. The lipid has a polar hydrophilic head group. It loves water. It's often electrically charged.
Yeah.
To flip to the other side, you have to drag that water-loving, charged head group through the deep, oily, hydrophobic center of the membrane.
It's like trying to drag a magnet through a block of rubber. There's a massive energy barrier.
A huge energy barrier. Leninger notes that without any help, a single phospholipid might flip-flop maybe once every few days, or even weeks.
So on a biological timescale, it effectively never happens on its own.
Right. But here's the catch. The cell needs it to happen.
Why? If it's so hard, why force it?
Well, for one, you synthesize new lipids on one side of the membrane in the endoplasmic reticulum. To make the membrane bigger, you have to move some of them to the other side. And also for signaling. We mentioned that asymmetry is crucial. There's a lipid called phosphatidylserine, for example, that is strictly kept on the inner leaflet facing the cytoplasm.
Okay, so it's an inside lipid. What happens if it gets to the outside?
If it appears on the outer leaflet, it is a universal, unambiguous signal to the immune system.
And what's the signal?
Eat me.
Seriously?
Yes. It's a signal for apoptosis, for programmed cell death. A macrophage sees phosphatidylserine on the outside of a cell and knows that cell is dying and needs to be cleared away. It's a death flag.
So if a lipid just randomly flip-flops by accident, your cell gets eaten.
Which is exactly why the cell has to control this process with absolute precision. It can't be left to chance.
So how does it do it? If it's thermodynamically forbidden, how does the cell break the rules?
With enzymes. It builds machines to do the job. And these enzymes have the best names in all of biology.
Flippases, floppases, and scrambloses.
It sounds like a Dr. Seuss book, doesn't it?
It really does. So what do they do?
They're wonderfully descriptive. Flippases move specific lipids from the outer leaflet to the inner leaflet. They flip them in.
Okay.
Floppases do the opposite. They move lipids from the inner leaflet to the outer one. They flop them out.
And scrambloses.
Scrambloses, as the name suggests, are less specific. They can move lipids in either direction, usually down their concentration gradient to randomize them. They scramble the distribution.
And the key here has to be energy, right? To move something against its will like that.
Absolutely. The flippases and floppases are active transporters. They burn ATP to do their job. They are using energy to actively fight against thermodynamics and maintain that crucial asymmetry.
So maintaining that difference between the inside face and the outside face of the membrane costs the cell energy.
Control always costs energy. That's a recurring theme.
Now, membranes aren't just flat sheets floating around. They have to curve, they form little buds that pinch off, they have to fuse with other membranes. How does a liquid sheet, two of them, actually fuse? I'm thinking about a neuron releasing neurotransmitters.
Yes, membrane fusion. This is pure mechanical magic at the nanoscale. So you have a neuron, and inside it, you have a little bubble, a vesicle, that's full of neurotransmitters like acetylcholine.
Okay, it's sitting at the synapse, waiting.
And it has to merge with the main plasma membrane to release its cargo. But there's a problem. Both membranes have negatively charged surfaces.
So they should repel each other like two magnets.
They do, and on top of that, you have to get rid of all the water molecules that are stuck to those surfaces. That hydration shell we keep talking about, it's very stable and very hard to remove.
So you have to overcome electrical repulsion and a physical water barrier. How?
You need a winch, a molecular winch. The cell uses a family of proteins called snares.
Snares.
Right. You have V snares on the vesicle membrane and T snares on the target plasma membrane. They are long helical proteins.
And they recognize each other.
They recognize each other, and when they get close, they start to coil around each other, forming this incredibly tight 4-helix bundle.
Like twisting two wires together.
Or zipping up a zipper. And as they coil, they pull with immense force. They are physically winching the two membranes together, overcoming that electrostatic repulsion and squeezing all the water out from between them.
So it's pure mechanical force.
It is. They pull and pull until the outer leaflets of the two membranes touch and fuse, and then the inner leaflets fuse, and suddenly you have a pore. The neurotransmitter spills out.
And what happens if that winch breaks?
Well, if your snares don't work, your nerves can't talk to your muscles. You're paralyzed. This is actually how botulinum toxin Botox works.
How?
The toxin gets inside your nerve endings, and it's a protease, an enzyme that cuts proteins, and its specific target is the snare proteins.
It cuts the winch cable.
Precisely. The vesicle is there, the signal to release is there, but the winch is broken. The vesicle can't fuse with the membrane, the muscle never gets the message to contract.
And that's why it smooths wrinkles. It's literally paralyzing the small muscles in the face.
Exactly. A powerful lesson in the mechanics of the membrane.
Okay, that is a sobering thought. Let's move on to the main event. The whole purpose of this intelligent interface. It's not just to exist, it's to control what comes in and what goes out. Section 3. The gatekeepers.
This is where we confront the permeability problem. That beautiful lipid bilayer we described is an excellent barrier. It's fantastic at blocking anything that's polar or has an electrical charge.
So, ions, sugars, amino acids, all the things the cell needs to eat.
All the good stuff, they just bounce right off. So a cell that was only enclosed by a perfect lipid bilayer would starve to death in a sea of nutrients.
So the cell has to install doors in the wall.
Exactly. And Leininger is extremely careful to make a critical distinction between the two main types of doors, channels and transporters.
I feel like in everyday conversation, people use those words interchangeably. You know, an ion channel transports ions.
And that's fine for casual chat. But biochemically, they are worlds apart in their mechanism. Let's start with ion channels.
These are the speed demons.
Right. They are unbelievably fast. A channel is essentially a tunnel. It's a continuous, water-filled pore that goes all the way through the membrane.
So when it's open, stuff can just flow right through.
And it flows at an incredible rate, something like 10 million to 100 million ions per second.
100 million per second.
It's a torrent. It's operating near the physical limit of free diffusion. It's like opening the floodgates of a dam.
And because it's just an open gate, they aren't saturable, right? You can't fill up a channel.
Correct. If you increase the concentration of ions outside, the flow rate through an open channel will just keep increasing.
But they're not just dumb holes.
Yeah.
They're incredibly picky about what they let through.
Extremely picky. And this brings us to what I think is my single favorite example of molecular engineering in all of Leininger, the potassium channel. Specifically the one from the bacterium Streptomyces lividans.
Ah, yes, the diagram of that is famous. It has to solve a paradox, doesn't it?
It does. This channel is amazing at letting potassium ions plus through, but it completely blocks sodium ions. None, null, or plus doll.
Okay, but if you look at the periodic table, sodium is smaller than potassium.
That's the paradox. If the hole is big enough to fit the bigger potassium ion, why doesn't the smaller sodium ion just slide right through? It's like building a doorway for a basketball. A golf ball should go through no problem.
So our intuition is wrong here.
At the molecular scale, intuition often fails. You have to remember the hydration shell, that water jacket that every ion wears in solution.
Right. To go through the narrowest part of the channel, the ion has to take that jacket off.
It has to shed its water molecules,
Yeah.
and that costs energy. It's an energetic penalty. The ion doesn't want to do it.
So you have to bribe it.
You have to give it something just as good in return, and that's what the channel does. The inside of the channel, the narrowest part called the selectivity filter, is lined with carbonyl oxygen atoms from the protein's backbone.
Okay, so a ring of oxygen atoms.
And these oxygens are positioned with angstrom-level precision. They are spaced exactly right to perfectly mimic the positions of the water molecules that normally surround a potassium ion.
So it's a perfect substitute.
It's a perfect chemical mimic. The potassium ion sheds its water, slides into the filter, and interacts with these protein oxygens. Energetically, it's a wash. It feels just as stable as it did when it was in the water.
It's been tricked. It doesn't even notice it took its water jacket off.
Exactly. Now try to push a sodium ion through. Sodium is smaller. When it enters that filter, the perfectly spaced oxygen atoms are too far apart for it.
It can't touch them all at the same time.
It can't. It's like a small child trying to climb a huge staircase. It can't bridge the gaps. So it cannot regain the energy it lost by shedding its water.
So it's energetically unfavorable for the sodium to enter. It prefers to just stay outside in the water.
That's it. The channel rejects sodium not because it's the wrong size, but because it's the wrong fit. Selectivity is all about the precision of that fit. It's just breathtakingly elegant.
It really is. Okay, so those are the super fast, super selective channels. Now let's contrast them with the other type of door, transporters.
Right. Transporters, which are also called carriers, are much, much slower. They operate more like an enzyme than a tunnel. We use the alternating beat model to describe them.
I think of an airlock on a spaceship.
That's a perfect analogy. You have an outer door and an inner door, and the crucial rule is that they are never both open at the same time.
Okay.
So a molecule, let's say glucose, comes from the outside and binds to a specific site on the transporter. That binding triggers the outer gate to close.
Click, the outer door shuts.
Then the entire protein undergoes a massive conformational change. It literally changes its shape, reorienting the binding site to now face the inside of the cell.
So it flips around.
And then the inner gate opens clunk, and the glucose is released into the cytoplasm.
So because every single molecule
Right.
requires this whole mechanical cycle of binding, shape change, release,
Yeah.
they must be way slower.
Orders of magnitude slower. We're talking maybe 100 to a few thousand molecules per second compared to the 100 million of a channel.
And they must be saturable.
Yes. Just like an enzyme has a maximum velocity, a Vmax, transporters can be completely overwhelmed. If all your airlocks are busy cycling, adding more people outside doesn't make the line move any faster.
Okay, so these channels and transporters can let things move downhill down their concentration gradient. That's passive transport. But we said life is a rebellion. Sometimes you have to push things up the hill.
And that brings us to Section 4, active transport.
This is where we have to start paying the energy bill.
Active transport is, by definition, moving a substance against its electrochemical gradient. That is an energetically unfavorable process. It has a positive delta G. You have to couple it to an energy source,
Usually ATP.
the energy currency of the cell.
Yeah.
And the undisputed king of ATP-powered pumps, the protein that arguably defines animal life, is the sodium-potassium pump, the non-all plus K plus 8T pace.
Right. Harper calls this the single most important transport protein in animal cells.
It absolutely is. It sets the stage for almost everything else. Its job is to pump 3 sodium ions, OUT of the cell, and 2 potassium ions, IN.
I remember the mnemonic from med school. 3 out, 2K in.
The stoichiometry is crucial. But the statistic that Harper drops that just floors me every time is the energy cost. This one single protein consumes roughly 1/3, 30% of a typical cell's entire ATP budget.
Wait, hang on. A third of all the energy from the food I eat, a third of the ATP from every breath I take, is just to power this one little pump, repeated over and over.
In some cells, it's even more. In an active neuron in your brain, it can be up to 70% of the total energy budget.
70%. Your brain is basically just a machine for running sodium-potassium pumps. Why? Why spend so much energy on this one task?
Because it's not just one task. By doing this, it creates a massive electrochemical gradient. It packs the outside of the cell with sodium. It turns the cell membrane into a charged battery.
It's like pumping water up a hill to fill a reservoir behind a dam. You're storing potential energy in that sodium gradient.
That is the perfect analogy. And once you've spent the energy to fill the dam, you can use the flow of that water back downhill to power all sorts of other machinery.
Ah, so that's secondary active transport.
Exactly. The cell can have a different transporter, say one for glucose. This transporter has a binding site for sodium and a binding site for glucose.
Okay.
It will only transport glucose if sodium binds at the same time. The sodium wants to rush into the cell down its steep gradient, and as it flows in, driven by the energy stored by the pump, it drags the glucose along with it, even if that means pulling glucose up its own concentration gradient.
So the glucose gets a free ride, piggybacking on the sodium that's rushing downhill.
Exactly. The pump doesn't use ATP directly, but it's completely dependent on the gradient established by the pump that does use ATP.
So the sodium-potassium pump is the master battery charger for the cell.
It is. It charges the battery that then powers nutrient uptake, it maintains cell volume by controlling osmolarity, and it sets the resting membrane potential that's essential for all your nerve impulses. If this pump stops, the battery dies, and the cell dies within minutes.
Speaking of other powerful pumps, we have to talk about the ABC transporters.
The ATP-binding cassette family. This is a huge, ancient superfamily of proteins. They're the heavy lifters. They pump everything from ions and amino acids to lipids and, importantly, drugs.
And this is where they often become the villain in a clinical story, especially in cancer therapy.
Yes. The most famous one is called MDR1, for multi-drug resistance protein 1. It's also known as P-glycoprotein.
And its normal job is protective, right?
A very important protective job. It's found in high levels in places like your intestinal lining and the blood-brain barrier. It recognizes a huge range of foreign hydrophobic molecules, toxins from your diet, for example, and it actively pumps them out of the cells.
Which is great until the cell is a cancer cell.
Exactly. Cancer cells are clever. Through mutation and selection, they can learn to massively overexpress this MDR1 pump. So you give a patient a chemotherapy drug, which is essentially a targeted poison.
Right.
The drug gets into the cancer cell, but before it can do its job, MDR1 recognizes it as a foreign toxin, grabs it, and uses ATP to physically throw it back out of the cell.
It just spits the medicine out.
It's like trying to sink a boat while the crew is bailing water out faster than you can pour it in. The cancer cell co-opts our own sophisticated defense machinery to survive the very thing that's supposed to kill it.
A tragic and brilliant example of the power of these membrane machines.
It is, and it really highlights that these aren't just pores. They are active, intelligent machines.
This leads us perfectly into our final section, the clinical implications. Because when these incredibly precise machines break, or when the genetic blueprint to build them is flawed, you get disease. And both Leninger and Harper point to cystic fibrosis as the textbook case study.
It's a fascinating and, frankly, heartbreaking story that all comes down to protein folding and quality control. The protein at fault is called CFTR.
The cystic fibrosis transmembrane conductance regulator. It's a mouthful.
It is. Now, if you look at the structure of CFTR, it looks for all the world like an ABC transporter. It has the same domains that bind ATP, just like the MDR1 pump we just discussed.
But it doesn't act like a pump.
That's the twist. It doesn't pump anything. It functions as a chloride ion channel. It lets chloride ions flow down their gradient. It's an evolutionary oddball that uses ATP not to push things uphill, but just to open and close the channel gate.
Okay, so its job is to be a chloride gate. What goes wrong in the disease?
The most common mutation, responsible for about 70% of cases, is called delta F508.
Which means?
It means a deletion. That's the delta of a single amino acid, phenylalanine, which has the one-letter code F at position 508 in the protein chain.
Just one amino acid is missing out of almost 1,500.
One single amino acid. And here is the absolute tragedy of the disease. That mutated protein, if you could somehow get it to the cell membrane, it would actually work. It's a bit crippled, but it can still transport chloride. It's functional.
So, why are the patients so sick if the channel works?
Because of the cell's internal quality control system.
Yeah.
That missing phenylalanine causes a tiny, subtle misfolding of the protein as it's being made in the endoplasmic reticulum. It's just a little bit wobbly.
And the cell detects that.
The cell's chaperone proteins, the quality control inspectors, they detect this tiny structural flaw. They decide it's a defective product.
And they reject it.
They tag it for destruction. It gets sent to the proteasome, which is the cell's paper shredder, and it's torn to pieces.
So the factory trash is a perfectly functional product because of a tiny scratch on the paint.
That's a great way to put it. The protein never even reaches the cell membrane where it's needed, so the end result is a complete absence of chloride transport.
And because the chloride ion can't move out of the cell.
Water doesn't follow it. You always have to remember that simple rule of osmosis. Water follows salt. In the epithelial cells of the lungs and pancreas, the whole point of secreting chloride is to draw water out, to hydrate the mucus layer.
But if the chloride is stuck inside, the water stays inside.
And the mucus on the outside becomes incredibly dehydrated. It turns from a thin, slippery liquid into a thick, sticky glue.
And that's what causes the problems.
That's the core pathology. In the lungs, that thick mucus traps bacteria, leading to chronic, life-threatening infections. In the pancreas, it blocks the ducts so digestive enzymes can't get out. It's a transport failure that leads to a hydration failure.
A devastating cascade from one missing amino acid. Harper has a whole list of these membrane-related diseases. Can we touch on hereditary spherocytosis? That sounds like a structural problem.
It is. It takes us right back to the architecture we started with. The cell membrane isn't just a floppy soap bubble. It's supported by an underlying protein scaffolding, the membrane cytoskeleton.
Okay.
In red blood cells, this scaffolding is made of proteins like spectrin and ankyrin, and this skeleton is what pulls the membrane into that classic biconcave disc shape, the donut without the hole.
And that shape is important for its function.
It's critical. That shape gives it a high surface area to volume ratio, which makes it incredibly flexible. It can fold in half to squeeze through the tiniest capillaries in your body.
So what happens in spherocytosis?
You have a mutation in one of those anchor proteins, like spectrin. The membrane detaches from the underlying skeleton. Without that tension pulling it inward, it relaxes into the most energetically stable shape for a given volume, which is a sphere.
And a sphere isn't flexible.
Not at all. It's taut, like an overinflated balloon. So when these fragile, spherical red blood cells try to squeeze through the narrow filters of the spleen, they get stuck and they burst. That's hemolysis.
It really drives home that the membrane is this complex, reinforced, engineered material.
It is. And just one last clinical angle. We've talked about what happens when our own proteins fail, but nature has also evolved weapons to attack the membrane.
You mean toxins?
Exactly. Many snake venoms, for instance, are just a cocktail of enzymes, and a key ingredient is often a phospholipase.
Which does what?
It's an enzyme that literally digests lipids. It chops the polar heads off to phospholipids. The membrane just disintegrates. The victim's tissues effectively dissolve as the cells spill their contents.
A terrifyingly direct attack. We've covered the architecture, the dynamics, the gates, the pumps, the diseases. It is a vast and intricate system.
It is the defining system of a cell. Without the membrane, you don't have a self. You just have chemical soup.
Which brings me to my final thought for you, the listener. A little bit of a philosophical provocation to end on. We've spent this entire deep dive talking about the membrane as the ultimate definer of the self. It's the wall that separates me from not me.
The boundary of life, yes.
But both Leininger and Harper mentioned something called a gap junction.
Ah, connexins.
Right. These are channels, but they're special. They're channels that physically connect the cytoplasm of one cell directly to the cytoplasm of its neighbor. They form a continuous tunnel between two cells.
They do, and through these tunnels, ions and small molecules can flow freely from one cell to the next.
So in your heart, for example, the electrical signal to contract can just zip from cell to cell through these junctions, so the whole muscle beats as one single unit.
A functional syncytium, yes.
So here's the question. If my cytoplasm can flow into your cytoplasm, are we still two separate cells? Or are we one big cell that just happens to have two nuclei? At what point does the boundary of the self start to blur?
That is the fundamental tension of being a multicellular organism. To build a tissue, to build a body, the individual cell has to surrender some of its autonomy. The membrane has to evolve from being a fortress wall to being a highly managed, semi-permeable connection point.
The border becomes a bridge.
The border becomes a bridge, and the definition of self expands to include the community.
The intelligent interface, indeed.
Indeed.
And that is our deep dive on biological membranes and transport.
Yes.
Believe it or not, we have barely scratched the surface of the biochemistry here.
Please, go look at the diagrams. Find the crystal structure of the potassium channel in Leininger. It's a genuine work of art. and browse the clinical tables in Hopper to see just how many things can go wrong with this system.
Thanks for listening. Stay curious.
We'll see you in the next one.